Hi there, today we're going to start by talking about SI units, what are they, and why do they matter. SI stands for Scientific International or Standard International Units, as I like to think of them, and they represent a global set of units that we use for science and technology. In fact, in 1999, there was a Mars probe that was lost, and it was lost due to the lack of conversion of units, and therefore, unfortunately, more than $125 million worth of effort burnt up in the Martian atmosphere as a result of lack of consistent units. This shows that we need a consistent and useful global set of units that everyone uses together. There are 7 fundamental units that we use as scientists in the universe. These are length, time, mass, current, amount of matter, temperature, and luminous intensity. And as you can see, I'm highlighting here, they're represented by meters, seconds, kilograms, amperes, moles, Kelvin, and candela, respectively. You may have heard of some of these, but I doubt you've heard of candela, which represents luminous intensity. These are particularly useful in the scientific community as they can be used to make up all the other units that you see or interact with in your studies. Now, apart from SI units, there are many other units which we call derived units. Some examples are shown here, which include area, volume, energy, velocity, acceleration, force, and power. These are just some examples, and you can see they can be made up of SI units. These SI units may be shown directly, such as the case with meters squared, meters cubed, meters per second, and meters per second squared. However, derived units can also be made of other SI units, and it does not show. Joules, newtons, and watts, for example, here highlighted in purple, are all derived units. However, they do not directly show the SI units that underlie them. But of course, you didn't come here just to find out about SI units, you came here to figure out why units are your friend. Now we're going to start with a simple equation, which is Newton's classic equation of F equals ma, which means force equals mass times acceleration. Now in this equation we have units. These units are represented in square brackets, and the units for force is equal to newtons. Notice that I'm going to show here that we use square brackets throughout the video in order to show units, and that's often how I will show units when discussing physics concepts, or any mathematics concepts really for science. When you consider mass has units of kilograms, and acceleration has units of meters per second, or meters per second squared. When you look at this, you can see that newtons is equal to kilograms multiplied by meters per second squared. And of course, overall, that means that newtons is equal to kilograms multiplied by meters divided by second squared. And that is in fact SI units, and that is the SI units for newtons. So force has this relationship with SI units that you see here. The next quantity we're going to talk about is kinetic energy. Now with kinetic energy, it relates to half mv squared. The m represents mass, and the v represents velocity. With kinetic energy, it has units of joules, because joules is the units of energy. Mass has the units of kilograms, and velocity has the units of meters squared. However, you'll notice here that I've left a little gap to put the squareds on top of the meters and the seconds, because since we're dealing with kinetic energy, we're dealing with velocity squared. I'm just going to redraw this out again for a second to show you the expanded units together. So joules for energy is equal to kilograms meters squared per second squared. So kilograms, meters times meters divided by seconds times seconds. And these are the SI units of energy itself. The reason we do this, and the reason that we want to understand about SI units, is that these can help us understand formulas, and when we get stuck, they can help us figure our way back to the original formulas themselves. The second formula that I want to consider is GPE, gravitational potential energy. And gravitational potential energy is shown by mgh, where m stands for mass, little g stands for the acceleration due to gravity, and h stands for the height above the surface of the Earth, or wherever you may be dropping the given object. Now this is really useful because GPE is another form of energy, and energy is again represented by joules. So this is a really good comparison against what we just did with kinetic energy, and it helps us to show that once again, joules can be represented by SI units. However, you get there in a different way, because before we were doing mass with velocity squared, and this time we're doing mass with acceleration and height. So here you see joules. Joules is equal to kilograms multiplied by meters per second, multiplied by meters, or meters per second squared, multiplied by meters. And notice that from the row before to the row below, you can see that the meters have multiplied together, and that has given you meters squared. And that ends up giving you kilograms meters squared divided by seconds squared. So now we're going to consider another example, which is momentum. Momentum is equal to force multiplied by the time, or change in time. But momentum is also equal to mass multiplied by the change in velocity for a given interaction. We can also think about the units of this situation, and the units for force are equal to newtons. You should also remember that force comes from mass multiplied by acceleration, and so we can also say that newtons are equal to kilograms multiplied by meters and divided by seconds squared, or kilograms meters per second squared. Time, or change in time, is equal to seconds, and so if we multiply that by the SI units, then what we'll find is that we get kilograms meters divided by seconds. No longer seconds squared, because now when you do the force with the time, it gives you the SI units for momentum, which is kilograms meters divided by seconds. What we can also see is if we consider the other side of the equation, which is momentum is equal to mass multiplied by the change in velocity. The units for mass are kilograms, the units for velocity are meters per second. And so once again, we see the SI units of momentum, which is kilograms multiplied by meters and divided by seconds. This just shows you how powerful unit analysis can be in relating the relationship between units and formulas. If we consider now power, such as electrical power or power used in reading any given device, power itself is equal to energy divided by time. And so if we consider the units of power is watts, the units of energy is joules, as we saw before, and the units of time is in seconds. So the units for power, which is watts, is the same as joules per second. It's the amount of energy that you use over a given amount of time. The more energy you use in a smaller amount of time, the greater the power that you have used or produced. But we also have power is equal to voltage times current, which is represented by a big V and a big I. This is so important because power is really versatile in showing the usefulness of relating units and being able to juggle different formulas with different units. So if we consider power is equal to voltage multiplied by current, I'm going to represent them here with different colors. Power is in yellow. You can see that it's represented by joules per second. Green is for voltage, and voltage is actually equal to energy divided by charge. So it's the energy per charge. We know the units for energy is in joules, and the units for charge is actually in coulombs. Then we also have current, which is represented in blue. Now current is equal to the amount of charge divided by the amount of time that has passed. So it's the charge that goes through a given point in space and time. So that is equal to coulombs divided by seconds. Now if we put this all together, at the bottom what we'll see is that joules per second from power, which is the same as watts, is equal to joules per coulomb multiplied by coulombs per second. And of course, when you consider that you have joules per coulomb and coulombs per second, if you look carefully, you'll see that the coulombs on top and the coulombs on bottom should cancel, and you'll end up with joules per second on both sides. So power is equal to voltage multiplied by current. And you can check that and verify it by using your units, and that helps you think about this situation. Finally, I just wanted to show one last time the relationship between power and voltage and current, because this can be written a completely different way. When you show power is equal to voltage times current, usually you would write watts, and you would write volts, and you would write amperes. And so the units usually have nothing to do with each other, and it's very hard to understand how they cancel and how the formula works. However, now you understand that in essence, SI units allow us to effectively and succinctly understand how formulas relate to one another, we can use them to better understand what's going on and how this works to help save us headspace and make our physics even better. If you like this video, please like and subscribe, and thank you so much for your time. Cheers and stay curious.